So discussion for this evening is mainly on my work, which I've done a few years back. And it's basically about the enhancing the stability of Cobalt Fischer Tropschcatalysts with boron promotion. Next slide, please. Okay, so I'll break it up into 5 segments. First of all, a short introduction, followed by research motivation. And then we'll discuss, I'll share with you all about the deactivation mechanism that is formally experienced with Fischer-Tropsch catalysts. And of course, we talk about the mitigation once we have discovered about the deactivation mechanism. Lastly, followed by summary and also conclusions. Next slide. If you are familiar with syngas production, you know that syngas can be produced from natural gas sources, which are primarily methane. So you go through steam methane reforming or catalytic partial oxidation. Or the more conventional route is coal, which we call it gasification. In fact, historically, coal was the preferred route used by Germany during prior to World War II and also to the end stages of World War II. That's how Germany fueled their war machines, primarily by using coal and converting them using iron catalysts to produce various fuel grades. And of course, of interest lately is biomass to liquid, or is also a form of gasification. And I think that biomass to produce various sources of hydrocarbon feeds and hydrocarbon cuts will be interesting as we transition away from fossil fuels and more renewable resources. And of course, from syngas is actually a combination of carbon monoxide, CO, and also hydrogen. And syngas will then go through Fischer-Tropsch synthesis. These days, cobalt or iron catalyst is still used, but primarily for cobalt catalyst, it's mainly used for natural gas feedstock. And from Fischer-Tropsch synthesis, you get various sorts of hydrocarbon cuts. The likes one being alkanes, right? Alkenes, and the heavier one will be the waxes. Next slide, please. Briefly about Fischer-Tropsch synthesis. As the name suggests, it was discovered by Franz Fischer and also Hans Tropsch in 1920s. And I have briefly discussed also that it converts a syngas to alkenes, alkanes, and small amounts of oxygenates. Various catalysts have been used: iron, cobalt, nickel, and ruthenium. And these are known to be very active for Fischer-Tropsch synthesis. Next slide. And of course, nickel, people have also used it, but it simply produces too much methane, and that's not very useful if you want to produce waxes. Ruthenium, extremely active, but at the same time too expensive, and globally there's limited supply. And we come back to the more common catalysts, which are iron and also cobalt. Now, cobalt is generally preferred due to lower water gas shift and also higher paraffinic products. And cobalt catalysts are anchored on oxidic support to maximize their performance. And the reason for anchoring them on various forms of inert supports is also to increase their dispersion so that their surface area is larger. Next slide. So this is a typical reaction, all right, normalized to 1. It's a slurry bubble column reactor, 100 barrels per day. It has been online for almost 2 months. And these are the typical Fischer-Tropsch conditions, realistic Fischer-Tropsch conditions, 230 degrees Celsius with a hydrogen to CO ratio of 2 and the pressures of 20 bar. And as you can see, right, the curve basically drops, the activity drops over time. Can you click on it? One click, please. And then this indicates that the activation is taking place on our cobalt catalyst. Next slide. Now, various mechanisms have been proposed. Almost 60% believes that it is due to oxidation, including cobalt-supported compounds. Next group after oxidation, sorry, can you go back? Yeah, thank you. So the next largest group believe that is due to carbon, including fouling by waxes. Next believe sintering. Sorry, can you go back? Yeah. Next believe that it is sintering, about 14%, and 10% is attributed to other deactivation mechanisms due to poisoning or attrition or reconstruction. Surprisingly, no oxidation has been observed for industrially relevant cobalt loadings, but gradual carbon buildup has been observed. Next slide. So what's the motivation and the impetus for cobalt catalysts and researching cobalt catalysts for Fischer Tropsch? I think firstly is to identify the deactivation mechanism, okay, during realistic Fischer Tropsch conditions. And secondly, is to identify what are the novel methods that can be used to actually deactivate, or rather to lengthen their lifespan. Now, this is very important because in the industry, whereby I'm a full-time in the industry, every time your catalyst deactivates, you have to spend an awful amount of time to actually regenerate it. So when you regenerate, when you put your catalyst on the regeneration stream, then you won't be able to produce products. So that's the reason for the impetus. We want to lengthen the lifespan of the catalyst before it comes to, or rather the deactivation is slowed down as much as it can before we regenerate it. Next slide. So in order to study the deactivation mechanism, we broke it up into both experimental and also theoretical studies. For the experiments, I spend time in the lab. I make my catalysts, all right? I calcine them and all the things that are related to experiments. I characterize all my catalysts, and I also load it up into reactors to test them. And the interesting part is that we supplement the experiments with density functional theory modeling. Move on. Next slide, please. Thank you. So for density functional theory, I use a Vienna Ab Initio simulation package, or the acronym is called VASP. It's a well-known modeling software among people who uses Ab Initio or molecular modeling. So it uses a periodic calculation with Paul pseudopotentials. And what I've used is a PBE exchange correlation functional. And I've also set the K-point grids as 551 and also 221. And for the catalyst model, I use a Cobalt at 111 for terrace and steps. I layered the slab within a 10 Armstrong vacuum layer, and I allow the top two layers to relax. Okay, next one. Next slide. Okay, first of all, we study the, from a theoretical point of view, the stability of carbon on cobalt surface by using the Gibbs free energy reaction, all right? So for surface carbon, all right, for surface CH, for surface CH2 species, you realize that as far as the reaction is concerned, surface CH and CH2 species are pretty decent. They're quite high, all right? I mean, compared to surface carbon. All right, then you have a subsurface carbon. Subsurface means that the carbon has diffused into the cobalt, all right? And then you have the famous P4G clock, and you have graphene. And you realize that the last two, which are P4G clock, as far as graphene, they're actually extremely stable structures, all right? So it gives us a flavor and an idea what sort of stable carbidic forms that can form on cobalt catalysts. And later on, when I show more slides on experiments, we will realize that to some extent, what we have discovered in experiments matches what we discovered from molecular modeling as well. Move on. Next slide. Okay, thank you. Yeah, next slide, please. So as I've stated earlier, the most stable species are P4G clock reconstructed carbides and graphene overlayers. And as you can see, right, perhaps it's a little bit not too obvious to you all, but basically this is a step cobalt catalyst. It's in a terrace form, All right, so what we did was we tried to understand how much more stable if we keep adding P4G clock reconstruction. So with one carbon, when it induces distortion to 4 cobalt atoms, you realize that the stability is about minus 43 kilojoules per mole. When we added the second layer, the stability actually increases to 92 kilojoules per mole. And lastly, you know, as we add on, it becomes 96 kilojoule per mole. So which means to say that if we keep adding any more P4G clock reconstruction, you'll probably stabilize about 90, 92 or 94. Meaning to say that it won't, there will be less thermodynamic impetus to actually form P4G clock along the terraces. Now, next we look into graphene formation, which is at the lower 3 diagrams. So started off with 1, which you can see is minus 20 kilojoules per mole. And then as we extend the graphene sheet and the graphene structure, the stability increases to minus 80 kilojoules per mole. And when the entire cobalt surface is saturated with graphene, that's it. We have a very stable carbon form, which is graphene. And for molecular modeling, it's about 116 kilojoules per mole. Please move on. Yep. So now we come to the experimental part. All right, so these are the tools which I've used to actually formulate my catalyst. All right. A is basically an apparatus that is used to impregnate the catalyst. All right. B is actually a calcine machine. Next. Okay. So my cobalt nitrate was mixed to gamma alumina to produce about 28% of cobalt. I've added in a trace amount of platinum mainly to improve its reducibility, and it was impregnated at room temperature for 2 hours. Next. And of course, once step 1 is completed, I move to step 2, which is basically overnight drying at 80 degrees C. And I calcine in air about 400 degrees C, and the crucible bed depth was about 0.5 centimeter. Next. All right, and the next equipment, click again, please. Yep, so this is temperature program reduction. Basically, it shows 2 profiles, profile A and profile B. Profile A is basically cobalt impregnated with 0.05 weight% of platinum. And for B, it is not promoted. And therefore, you can see that from the area under the curve, right, especially for profile A, you see that firstly, more cobalt has been reduced. That's number 1. And number 2, the calcine peak temperatures for the unpromoted curve, which is in curve B, the peaks occurred at 310 as well as 580 degrees Celsius respectively. Once you add in a trace amount of platinum, it shift back the reduction temperature to 260 and also to 430 degrees C. And at the same time, it allows more cobalt to be reduced. So this is important because you want more cobalt which are active on the surface of the inert support to be able to perform its reaction. So a trace amount of platinum is more than enough. Anything more than 0.05%, you would have wasted your platinum. But of course, besides platinum, there are various other metals that can be added to improve its reducibility. You can add in ruthenium, for instance. But again, I mentioned earlier, ruthenium itself is very expensive, and also it's quite limited globally. Okay, next slide, please. Click. Yes, okay. So the next one is basically diffuse reflectance infrared Fourier transform spectroscopy, or we call it drifts. Basically, this is where for cobalt catalyst that has been reduced, we introduce carbon monoxide, and it will absorb onto its surface. And we can see from the drifts, right, the CO molecule stretching peak at 2045 centimeter inverse of 1. So it's a linear atopside. Why we are confident that this CO is mounted linear is because it's exactly at 2045 wave number. Next slide. Click again. And of course, this is for our X-ray diffraction. So for our XRD, our particle size is about 13.6 nanometer. All right. And then we use hydrogen chemisorption. We found that the diameter is about 10.5 nanometer with a dispersion of close to 10%. Of course, part of the reason for using hydrogen chemisorption is also to calculate the dispersion. So the hydrogen uptake means that the amount of hydrogen that it consumes is about 161 millimole per gram of a catalyst. Move on. Next slide, please. Okay, this is the most interesting part. This is a fixed bed reactor. It is quite large, and it's situated inside a specially built chamber for high pressure applications. And this is where Fischer-Tropsch synthesis at realistic conditions are conducted. So we have at least, right, minimum of 4 gases here: nitrogen per each, air. Of course, of interest will be hydrogen and also CO. And for hydrogen, CO, as well as primarily hydrogen and CO, they have to have a mass flow controller so that we can actually monitor their flow and control them. And of course, the reactions will go through the catalysts that are mounted inside the fixed bed reactor. Next slide. So these are our results. So this is a unpromoted catalyst, all right? The red dots time on stream for 200 hours at realistic Fischer-Tropsch conditions. You realize that there is a rapid deactivation phase, all right, followed by a slower deactivation phase. So what we did was we basically tried to understand, right, why deactivation is happening. We know that deactivation can happen. There are a number of mechanisms that has been proposed. But we want to see if it's really oxidation. You know, we believe that there is another form of a deactivation taking place. So basically, for the activity and selectivity table, you can see that CO conversion, right, at 25 hours is 96, and then after 200 hours it dropped down to 67. And the turnover frequency correspondingly shows that at 25 hours and also 200 hours it also reduced. In fact, all the carbon chains, C1, C2 to 4, C5 plus also reduced. Of course, the alpha chain increased a little bit. You notice that after the reaction, initial reaction and after reaction, I took the catalyst out and I tried to understand and characterize to see if there's appreciable differences in their particle size. There is a slight increase in their size from 10.5 nanometer to 12.1, and the dispersion from 9.5 has also reduced to 8%. Next one. Okay, so what I did with the cobalt catalyst after a reaction is basically to study them and to characterize them. First off, we start off with XPS. So the XPS curves are at the first one on top. You have a red profile as well as the black profile. The black profile is a catalyst after calcination. So it's a clean catalyst. Basically, it has been calcined. You see the peak at 284.8. And then you have a catalyst extracted from the reactor after Fischer-Tropsch synthesis. There are 2 peaks there, 283 as well as 284.6. So the peak at 284.8 has shifted a little bit to the 284.6. And if you notice, comparatively, the area under the curve has also increased significantly. And if you look at the temperature program hydrogenation, we realize that as I try to remove the carbons that have been built up on the surface of the catalyst, temperatures above 400 degrees indicates that these carbons are getting harder to remove using hydrogen. And it also indicates that there are very resilient types of carbons on the catalyst surface. And more interesting is the fact that when I took out the catalyst and I put them under TEM, I found two types of carbon. The circle one is an amorphous carbon. They're not well defined in terms of their shape. But the lower left, all right, which I indicated as a bar, these are very well defined shapes. And when I measured their spacing, it is about 0.33 nanometer. Okay, so this 0.33 nanometer is very interesting because it indicates that's the typical spacing commonly found in graphene structures or graphitic structures. Move on. Next slide. Thank you. So from our studies, we realized that deactivation is happening. We know that. A lot of people have mentioned, a lot of people studied and they believe that it's mainly due to oxidation, but our studies indicated that carbon is actually the source of all these deactivation. We have our experiments to prove, and we also have images to suggest that carbons have been observed on the cobalt catalyst. Now, the next question is, can we do something about the deleterious effect of carbon? Can we improve the stability of cobalt catalysts during Fischer-Tropsch synthesis? That's the second part of the study. Next slide. In the early days, we found that boron, when we dope to nickel catalyst for steam methane reforming, interestingly, boron was able to reduce a lot of coking on nickel catalysts. So both from density functional theory as well as experiments, we found that when nickel catalysts were doped with boron, it was much stable compared to the unpromoted nickel catalysts. So with this, we decided to implement the same strategy. Could cobalt catalyst doped with boron also improve its stability? Next slide. Next slide, please. So let's start back and go back to theory again. So we studied the stability of boron and cobalt surface, and we found that of interest at the step sites, boron do cling to the slab sites of a cobalt catalyst. In fact, it likes to form boron to boron interaction because it increases the stability on the cobalt catalyst surface. But that's only on the step sites. What about P4G clock? So earlier with cobalt catalyst with carbon, we have showed, right, that carbon also induces a P4G clock reconstruction on the cobalt catalyst. And surprisingly, boron also induces the same reconstruction on cobalt catalyst. And we realized that, you know, boron forms a very stable P4G clock reconstruction. And it surprisingly mimics carbon binding preference, both at the steps and also at the P4G clock reconstruction. Next slide. Now that we have studied briefly on the stability of boron on cobalt catalyst, what will be its effect, you know, towards carbon if we promote the cobalt catalyst with boron? And on the step sites, when we place boron at the clock, right, we realize that firstly, carbon reduced by 90, it becomes unstable, right? So positive 99 kilojoules per mole means it's unstable. And when we investigated carbon, all right, at P4G clock sites, again, it is unstable. So in other words, we realized that once we dope cobalt catalyst with boron, all right, it makes carbon very unstable at step sites as well as nearby P4G clock sites. And surprisingly, you know, even a small amount of boron at step makes carbon at step sites highly unstable. All right. So all these density functional theory studies basically indicates that, you know, when we have boron doped to doped to cobalt catalyst, it destabilizes the formation of a carbon on cobalt catalyst. So This gives us an idea, and that leads us to the experimental part. Next slide. All right. Okay. Before we move to the experiments, we have to discuss also a bit on boron, the effect of boron on the migration of carbon from terrace to step sites. When we started off by carbon itself, when it's on the terrace, all right, it has a preference to move to the step sites. In fact, we found that step sites are the locations for graphene to actually grow. And once graphene has grown out from those surfaces, especially the nucleating sites, which are identified as the step sites, it will basically kill off the catalyst. So what we found out that about carbon is that it has a preference to move to the step sites. Okay, our calculation shows that it is about minus 57 kilojoules per mole. Right. Moving on to boron. Once boron have formed a P4G clock reconstruction on the cobalt catalyst, you know, carbon becomes unstable. It is unable to actually absorb itself onto the cobalt step surface. As you can see from the calculation, it becomes unstable. It's not stable at all. So these are very interesting findings from our density functional theory. Next slide. So these are catalysts, cobalt catalysts that has been calcined and impregnated with various concentration of boron. All right, starting with the black profile, B2.0 calcine means that boron at 2% concentration was added to cobalt catalyst, followed by 1% and 0.5%. You will realize that the corresponding peaks, right, reduce in intensity with a reduction in boron. The peak at 191 EV is due to boron oxide, and the peak at 188.1 is due to cobalt boride. When we decompose the curves, we found that about 10% of boron oxide will reduce. And do note that only boron atoms interacting with cobalt particles can be reduced. Schematically, how we presented it is that we believe that boron is on the surface of the cobalt catalyst, although there will also be some portion of boron oxide on the alumina surface. But the boron oxide on the alumina surface is not taking part in the reaction. Only the boron, small amount, interacting with cobalt will be the one that is effective in managing carbon deposition. Next slide, please. Next slide. Yes, thank you. We performed drifts study again. So for the drift study, as you can see, there are 3 profiles here. Unpromoted, that's A. B is promoted with 0.58% of boron, and C is, of course, with 2% with boron. Now, it gives us an indication because, between A and B, there is a very little change in the area under the curve. Drifts, this is using CO drifts. That indicates, right, at 0.58%, there is no appreciable loss in the active sites on the cobalt when you compare it with A, which is unpromoted. On the other hand, if you add in too much boron, you realize that C, quite a significant amount of cobalt is unable to absorb CO, which also means that too much of a good stuff can be deleterious by itself. Okay. And in fact, if you see the hydrogen uptake table, right, the unpromoted is about 161 micromole per gram of catalyst. Slight reduction when you've promoted it with a small amount of boron. At 0.5, the hydrogen uptake reduced to 148, but with 2% boron, it's about 121. But the CO drift intensity significantly reduced a lot. Then if you look at the temperature per gram reduction, which is the second second chart beneath, again, we have 3 profiles. A is unpromoted, all right. B is 0.58% boron, and C is with 2% boron. Okay, so our conclusion basically suggests that if you dope cobalt catalyst with 0.58% boron, it has limited effect on its CO drifts, hydrogen uptake, and also on the temperature program reduction. 28% boron reduces the CO drifts, reduces the hydrogen uptake, and also increase the peak temperatures in TPR. When what I mean by peak temperatures in TPR, especially if you look at C, right, the blue curve, you have two peaks, 325 degrees C and 475 degrees C. If you compare profile C with profile A, you realize that they have shifted to the right-hand side, which means to say that if you add in too much boron, your cobalt gets harder to be reduced. Whereas for B, if you dope with only a small amount of boron, although there is some shift, it is not as bad as the one doped with 28% boron. Next slide, please. Now, this is the same experiment in a reactor. So the red dots are all the catalysts, cobalt catalysts that are undoped with anything, without any promoters. And the blue profile, the blue dots are the one that is doped with a 0.58% boron. It's interesting that just a small amount of boron, and we run the Fischer Trop in the reactor for 200 hours. And the deactivation rate coefficient suggests that it has slowed down significantly. All right. So the brief summary is that 0.58% boron reduces the activation rate by a factor of 6. And CO conversion is still maintained at 90%. And hydrocarbon selectivity is mainly unaffected. So this is important, especially from industrial point of view. A small amount of boron as a dopant can stabilize the catalyst for a longer period of time. And the good news is that there is little change in your product selectivity. Next slide. And of course, after the reaction, we took out the catalyst again and we put them through XPS. The red curve is unpromoted. The blue curve is promoted with 0.58% boron. And of course, the gray curve is the calcine. So we realized that promotion with 0.58% boron, it reduces the XPS intensity. And the peak at 283 and also 284.6 EV. Previously, it was detected, but now it is undetectable. So that goes to say that, you know, the small amount of boron actually prevented the growth of certain carbons on the catalyst surface. And if you look at the temperature program hydrogenation curves, right, between the red, which is unpromoted, and the blue, all right, the cutoff at 400 degrees C. Anything that is above 400 degrees C, if you burn it with hydrogen, it basically indicates that there are very resilient carbon deposits. And interestingly, the total amount of methane that came out from this TPH, you know, profile greatly reduced. And we can see also that there are less resilient carbons that are formed. Next slide. Okay, this is my last slide. Coming to the summary and also the conclusion. So, point number one, thermodynamic calculations identified two forms of stable carbon on cobalt, a P4G surface carbide and a polyaromatic carbon. And these two forms of carbon were also observed in XPS. Point number two is that boron mimics the binding characteristics of carbon. It is stable on the cobalt and can selectively block the nucleation sites. The nucleation sites are actually the step sites. Fischer Trop experiments confirms that when you dope a small amount of boron, in this case it's 0.58%, it basically reduces the deactivation by 6 times what we have seen from the experiments, and without affecting much of its selectivity. And point number 4 is that first principle modeling, in this case I've used VAS, can assist and guide chemical intuition for kinetic modeling and the design of catalysts. In the past, you know, when I say in the past, I'm referring to 100 years ago. Without such molecular tools, scientists have to resort to trial and error. to find the right catalyst, to find the right dopant. But with the power of computation, and I believe that, given more time, the molecular modeling tool will become even more powerful for us to perform all sorts of screenings. And of course, for experiments and also for theory to be successful, you need to know both aspects very well so that you can actually synergize their results together. And at the end of the day, whatever that is found from molecular modeling needs to be validated with experiments. And in my study, in my research, I'm glad that whatever that we studied from density functional theory was proven in experiments. Okay, I think that's my last slide. I think, can you move one more? I think that's to showcase one more slide, please. Yeah, just click. Yep, thank you. This is the background of Curtin campus. Just want to share with you all that I'm actually a part-time staff in this university. I'm actually a full-time engineer with the upstream oil and gas. But I'm glad that I can share my work with you all. Please ask me questions if you are interested to know more about my work.